Good morning. Let's wait for a few minutes, just 1 minute. Get others join in. So this is the syllabus for the coming test, 23rd and 24th, which is next Friday. Yeah, exactly 1 week. Okay, so all the concepts are covered. The last one is DP of this, and after that I did energy stored in the conductor. Okay, so any doubts before others join in? If you have doubts, you can ask me. And there is one more test, right? Board exam, CBSE. That's on Saturday. Okay, magnetic effect of current. That is the previous topic which is studied for this in IPL. Okay, so if you have doubts in this also, you can ask me.
So can you just show that syllabus for 1 second?
Sorry?
Can you just show the CBSE syllabus for objective testing?
CBSE syllabus is based on NCERT, right? I'll just open the NCERT book. Just a minute. Yeah, this is chapter. Actually, I would look at the latest NCERT book. This is, I think, a little bit. Just a minute. This is 24-25, right? It was the previous one. It was 24-25. Chapter number 12, I think. Chapter number 12. Okay. So first is basically this is a two-state experiment. This person basically if there are okay. There is a current carrying circuit is there. There is a conductor here, and you are placing a magnetic needle close to this conductor. So the current is flowing this conductor. The magnetic needle will deflect. If there is no current, means there is zero deflection. Once the current starts flowing, there is reflection. Another thing is if you reverse the direction of the current, then the reflection is the opposite direction. So the similar effect you can find between two bar magnets. If you place two bar magnets, North Pole close to each other, they'll repel, and North Pole and South Pole close to each other, they'll attract. And this magnet is basically a bar magnet. So and here you are seeing the same effect with having a bar magnet and the current. So the conclusion is current is like a bar magnet, or you can say source of the magnetic field is current. So this is the main conclusion of this person's experiment. Okay, accidentally this curved compass needle got deflected when electric current passed through the magnetic wire placed nearby. Okay, observations showed, okay, this is fine. Basically, I will say the conclusion here is that current is equal to a bar magnet. From that, we can get the conclusion that the source of the magnetic field. Sorry? You said something? Okay. Second one, magnetic field and magnetic field lines. Magnetic field is a region around the bar magnet where you find the effect of it. And so this is a bar magnet. So the field lines will look like this. So suppose if you draw the magnetic field vectors around this bar magnet, it will be strong near here. So hold on. So this is a bar magnet, right? So the rule for drawing the field lines is first you have to draw the vectors. So here at this point, the magnetic field will be like this, okay, and this of some strength. As you go out, the field in the strength will decrease. Okay. Similarly, here the magnetic field will look like this. Okay, here the magnetic field will look like this. And to get the strength of the magnetic field, basically we need a compass, magnetic compass. This is nothing but a bar magnet. We have north pole and south pole. Okay, if the strength of the magnetic field is more, means the deflection of this bar magnet will be more. Say theta, the deflection will be more. So from that we can get the strength of the magnetic field, and the direction of the magnetic field is the direction of the needle. So here the magnetic needle will look like this. Okay, here the magnetic needle will look like this. This will be north pole. Here the north pole will be here. So magnetic field is a vector, so we need both direction and magnitude. Direction of the magnetic field is the direction of this north pole, north and south pole. And the strength of the magnetic field is the amount of deflection, theta. Okay, so there is a way to find the magnetic field direction and the strength. So if you draw all these vectors, we'll get a vector field. Okay, and the rule for drawing these lines is first you have to these field lines. Here will be magnetic field lines. It should be tangent to all the vectors. It should be tangent to P vectors. Okay. Another rule is the line should be more if the magnetic field strength is more. Or density of lines is proportional to the strength of the magnetic field. So here the magnetic field, see as far as vector is concerned, if the magnetic field strength is more, means the length of the vector will be more. Okay. And direction is the direction of the arrow. Here, direction is the tangent to the field line. Okay. And the strength is proportional to the density of the lines. So here at this point, here in this region, the density is more, right? So field strength is more here. So as you go out here, compared to this one, the density of the field lines has decreased. So the magnetic field strength has also decreased. Okay. So here if you place the compression, the reflection will be less compared to the reflection here. Okay. Similarly here compared to here, the reflection here will be less. Okay. So if you try to draw the curve which is tangent to all the vectors, you will get these field lines. Okay, and you can put a arrow on this field line coincident with the direction of the magnetic field. Since the direction of the magnetic field here is like this, put a arrow in this field line consistent with that direction. Okay, so given the field line, I can get the magnetic field by drawing the tangent. So once the field line is given at this point, see at this point, if you have to get the magnetic field, first thing is draw a tangent. Okay, and direction of the tangent is the same with the direction of the arrow in this field line. So it will be like this, and the length of this vector is proportional to the density of the field lines here. So here, draw the similar thing here. Here will be longer. The vector will be longer. Okay, so this is the concept of field lines. So field lines give the idea of the strength of the magnetic field. If the lines are more dense, means the magnetic field there is more. Okay, and direction of magnetic field is coincident with the direction that's put on the field line. So here you can see, if you drawn it properly, the north pole south, the north-south direction coincides with this curve direction. Okay, so here you can see it's horizontal, right? Here it's almost at this angle. And magnetic field current connector, yeah, this one. Okay, and in 12th standard, whatever you learned integrated, we can get this magnetic field by using Ampere's second law. Okay, this is the conducting not conducting, it's a closed loop. Okay, so integral B dot dl along this closed path or contour, it's mu naught into current enclosed. So Ampere's circular law, integral B dot dl around the closed path is equal to mu naught into the current enclosed within this. Once there is a contour, see, we have an area. I is the current passing through this area. Okay, so here B is B and DL directions are same. That we can have to get by thumb rule. That we should have a prior knowledge of how the magnetic field lines will look. Okay, for a straight conductor, the field lines will look like this. So here, so here the current is downwards, right? So current is downwards, so thumb is pointing down. So the remaining four fingers will give me the direction of the current. That is the thumb rule. This one. Thumb is right hand. When you're applying thumb rule, you have two directions. One is the straight direction denoted by the thumb. Another is the curved direction or the circular direction. Okay. So when the current is in the direction of the thumb, the remaining four fingers will give me the direction of the magnetic field. So using this rule, right hand rule, we can say here the current is going down. So thumb should point downwards, and the remaining four fingers will point in this direction. So this is the direction of the magnet. This one. Okay. So it will be in the direction shown by the arrow, and I can choose the direction of the contour coinciding with the direction of the arrow. This C contour has got a direction, so I can choose the direction of the contour in the same direction as the magnetic field. So in this case, the angle between B and DL is, that's true for all points. Any point, the direction of the contour, I can say the DL. Okay, it's tangential. Even the magnetic field is tangent. The angle between B and DL is cos 0 degrees, and cos 0 degrees is 1. And B is uniform for all the points for a given contour, which is a circle of a given radius. And the center of the circle coincides with this conducting wire. So magnetic field strength B as a magnitude is constant. So B will come out the integral sign, which is integral DL. And integral DL is all the DLs adding up. So that is all the lengths adding up. That's the total length. So it will be into 2 pi r, where r is the radius of this contour. That will be equal to mu naught into I. From this I get P as mu naught I by 2 pi r. So magnetic field strength is more, the current is more. Obviously, if the source is stronger, means current will be stronger. And as you go far away, magnetic field will go down as 1 by r. So before applying Ampere's circular law, we should have prior knowledge of the direction of the magnetic field and how the magnetic field will look. After that, if you use Ampere's circular law, you will get this exact variation. That variation is 1 by r, and with the current is proportional to the current. This will get by applying Ampere's circular law. But we should have a prior knowledge of how the field line will look. One thing is obvious by symmetry, it should look symmetric about this current. And after that, we should use this thumb rule, okay, to get the direction of the magnetic field. So with that, we can, here there is no derivation for the in 10th standard. Just they are given the magnetic field direction look like this. Okay, and if you put iron filings around this conductor, okay, once the current passes, there will be magnetic field, and these small filings will behave like a small induced bar magnet. So they align this particular circular in a circular pattern. Similarly, instead of having a straight current, okay, we can have a circular current. current is entering here, the lower part, going like this, coming out like this. Okay. So this also produces a magnetic field. For this also, you can use the thumb rule. But here the difference will be, here the current is circular. So the direction of the current is, the direction of these four fingers. Okay. For straight current, it's opposite. Thumb will be the current and the fingers, four fingers will be the magnetic field. But for circular current, the circular direction is the current. Okay. And the thumb will give the direction of the magnetic field. So here, the current is going this way. Okay. So this figure has to be drawn properly. So the current is going. So then you get the direction of the magnetic field. Thumb is towards right, right? So the current should be going like this. Okay. This front part of the conductor is visible, and this back side of the conductor, what should I say? This is paper, right? So half the circle will be coming out, and half the circle will be behind the paper. Okay. So, or behind the screen. Okay. So this is the front part. So the current is going. I think I'm right. Okay. Yeah. The current is going up. Or if you assume this dark part is the front part, then you are correct. Because here he has put the current like this. Okay. So the current will go like this. And here will come out like this. Okay. So this dark part is the current, which is behind. Okay. So this light part is the one which is visible to me. Here the current will be like this. Okay. I'm getting confused. Okay. So, okay, there's only one thing you have to decide. This dark portion is this coil, they have put one half as dark, other half is light. Okay. So you have to figure out which one is on the front side, which is the back side. Okay, since the current is this one, the current is flowing this way. So the one, yeah, I think the dark portion is outside, which is visible to me. The light portion is behind. Don't get confused with this one. So you have to use a thumb rule to get the direction of the current. To simplify it. So this is the front portion of the coil, which is visible to me, and the current is flowing like this. Is the back portion, which is behind. So here the direction of the magnetic field will be towards right. Okay, if you use the right hand thumb rule, the four fingers will be the direction of the current, and magnetic field is towards right. Okay, so when the current is upward means the current magnetic will be towards left. Okay, so if the current here is upwards means behind is upwards, in front it is down. So here the magnetic field is towards right. Okay. This is same as this one because the one which is visible, the current is down. These two are same. Okay. In this figure, there is confusion, which is the one which is outside, which is the one which is inside. But this is the basic idea. So this is for a single circular loop, and here also you should have an idea of the magnetic field. It will look like this. Okay. So when you have multiple circular coils, the total magnetic field will look like this. Okay. So here, inside this solenoid, in the middle part, the B field is approximately uniform. See, for a single circular loop, the field will look like this. So from this, you have to figure out that If you put the second circle, here we'll get more strength. So in the middle, the field will look like this. So the thing that should be noticed is field is uniform. Okay, so from this I can suppose I want to create uniform magnetic field. The easiest way to get is have a solenoid, and the region, if I just stay within this region close to the axis and inside the solenoid, then the field will be approximately uniform. So to create uniform magnetic field, I'll take a solenoid and restrict myself to this region, which is within the solenoid and close to the axis. So in this region, the magnetic field is approximately uniform.
Sir,
Yeah.
if you keep a magnet inside a solenoid, it will get magnetized, no, sir?
Actually, they keep a soft iron core like this. That's actually creating a path for the magnetic field lines to flow easily. Like current
Okay, sir.
in a particular channel, that's the conductor, right? Similarly, if you have a magnetic field, I can create a space in, I can create a region where the field lines can pass easily. Okay, so that is soft iron core. That's called magnetic permeability. So
Okay, sir.
so for soft iron, the magnetic permeability is high. That means it allows the magnetic field to pass through it easily. Okay, that's what is done in transformers. In transformer, you have one coil called the primary, in which you pass the current I1. Okay, and you have to use this input to produce the current here, I2. So whatever flux is being, if it has to be efficient, means whatever flux is getting, okay, the way it's, this thing is getting clear, this will produce a magnetic field, okay, which will link this second coil, and if this magnetic field is a function of time, the flux linking the second coil will be a function of time. From that, I'll get the induced EMF of the second coil by Faraday's law. Okay, so for this whole thing to be efficient, I mean, whatever magnetic field is coming out of this first one should link the second one. Otherwise, there is wastage of whatever field lines and also energy, right? So to avoid that, to increase the efficiency, we have to make sure that all the field lines coming out of the first one should link the second one. That is done by inserting a soft iron core. If you have something like this, which is made of soft iron, okay. So this is like a conductor of magnetic field lines. So all the field lines which are outside, they'll come within this thing only. Okay. So if you do something like this, the field lines produced by this first one will link the second one. So that way, there is no loss of magnetic field. So you get the maximum efficiency. So this software and code inside will make the magnetic field to get focused within this software and code. This chapter is magnetic effect of current, right? Okay, so current carrying conductor in a magnetic field will experience a force that leads to here. We don't, okay, here there is no formula, but integrated course we studied that formula, right? The force on a current carrying conductor created magnetic field is its ideal cross B. Force on a current element TL carrying a current I when there's an external magnetic field. Okay, is ideal cross B. This comes from Lorentz force, which is B cross B. Okay, from this will get this thing. Okay, this comes from X1. Lorentz force is force on a charge move with the velocity through the magnetic field. Okay, when you have a current, there are charges flowing inside this, basically electrons. They will experience a force, and that force will give the force on the conductor, because inside the conductor there are a lot of electrons. So each electron will have a force, and each electron is same because the velocity of all the electrons are same, and external magnetic field is also same. So all the electrons will experience the force in the same direction to give a net force in a particular direction. That force is ideal cross field, and this can be derived. But for tension, it's not required. Okay, you just have to get the direction of the magnetic field using the thumb rule, left hand rule. That means left hand rule. So the first finger is the field, middle finger is the current, and the thumb will give the direction of the force. Okay, but here in integrated force, we know the direction of force is ideal cross B. Okay, so if you use that here, ideal is this one, B is this one. So ideal cross B is the thumb direction. Okay, see that that's what, if you know vector cross product, you don't need this thumb rule and all. But for tension and square, I will ask question based on that. The direction of the force is ideal cross B. If you use that thing here, okay, ideal is this one, B. So ideal cross B is towards left. So for example, this one, electron enters the region of magnetic field, right angles to its electron is going down and magnetic field is towards right. The direction of the force acting on the electron will be. So here you can use the Fleming's left hand rule. Field is the first finger. So your index finger is towards right. Okay. And middle finger is the current. Electron is moving down and electron is negatively charged. So the current is upwards. So once the current is upward, the thumb is pointing inwards. So the direction of the force will be into the paper. Use the Fleming's left hand rule. One way to remember is the field F is there, no? So that corresponds to the first finger. Okay. Middle finger is correct. So if you remember these two, you remember thumb as the motion. So the field is towards right. Okay. So your index finger should be towards right. And the electron is moving down. The electron is negatively charged. So the current direction is opposite. So current is upwards. So middle finger should go up. So if you hold it properly, then the thumb will point inside. Option D. Okay. Otherwise, you can use this ideal cross B. Ideal is upwards. B is towards right. So ideal cross B is into the paper. Ideal is upward. B is towards right. So ideal cross B is into the paper. Domestic subjects. Okay, have they covered this in electricity chapter? No, most probably not.
No, sir. Only up to human eyes, sir.
Yeah. So basically, there will be a obviously there has to be a positive terminal and negative terminal, right? Current will lead the enter by a positive terminal and lead the negative terminal. So here, this is the live wire, which is the positive wire, and neutral. The current will return via this wire. Okay. So the path of the current will flow is like this. This is red wire. Okay, and it passes the devices, and when it's coming out, it comes to this black wire and this one. And there's a potential difference of 220 volts between this positive wire and the negative wire. Okay, and it's safe to have an additional wire, earth wire. Okay, and then connect it to the negative, because this thing is putting only a potential difference of 220. The potential difference of 220 means it can be just the difference is 220. The exact value of the potential can be different. That's 10 minutes. Hold on. the potential difference between positive and negative wires is 220. That means the potential here,
Okay.
one way to get it is
Not down.
this can be 0 volts. Okay, this can be 220 volts.
The books and the lesson allowing this call.
This is say 100 volts. Okay, then this thing be 320 volts. Okay, and suppose here a person is standing here. Okay, his feet is on the ground. Okay, suppose this guy touches this live wire, then the potential difference which
Yes,
is, suppose this was the first case, then it will be 220 volts. So the potential effect across this person will be 220 volts. But if this person touches this wire, when this negative wire is at 100 volts, then he'll experience a potential difference of 320 volts with a radial shock. Okay, so basically, if you make sure this this potential is same as the earth potential, then the potential difference which this person will experience when he touches live wire is just 220 volts. That way, the amount of shock this person experience will be safe. It won't be high. So this is the main purpose of having this earth wire. Okay, when this earth wire is not there, then this potential of this negative wire can be anything. It can be also be 1000 volts. Okay, in that case, the live wire will be at 1220 volts. And when this person touches this wire, he'll experience a potential difference of 1220 because his 1 feet is no ground, which is 0 volts. Okay, so this is the main purpose of using this earth wire. Another thing is, if there is too much of current flowing, means there's one more thing called fuse. Okay, suppose accidentally, and another thing of this domestic electric circuit is all the devices will be connected between this live wire and this negative terminal. So any device we have will experience a potential difference of 220 volts. Okay, suppose you want to have reduced voltage, means then you have to use a step down transformer. But whatever plug point is available in the wall circuit boards, between those two terminals, positive and negative terminals, it will only be 220 volts. But the current here will get added up. Suppose say this is device 1. There's a plug, we have shown as plug 1, but this plug 1 I can't get anything. Suppose this is connected to fan, and this to light, and this to TV. Okay, all these devices will have the same voltage difference across it. This 220 volts. Okay, but the current drawn will be different depending on the wattage of the device. And the total current here will be the sum of these currents, I1 plus I2 plus I3. But this wire will have a capacity that it cannot, if it carries too high a current, once current passes through the conductor, ideally its resistance is 0, but in the reality, it has some small resistance. So this conductor will get heated up, and the amount of heating is I square R. For a resistance, the power dissipated is V into I, that can also be written as I square R. Okay, so if this R of the conductor, this wire is fixed. So if this current becomes too high, the heating will be more, so this wire will start melting. So to avoid this thing from happening, I'll have a fuse wire here. Okay, fuse wire. So this fuse will also get heated up. Suppose the current is too high, if the fuse wire melts before, and then the circuit breaks before this actual wire melting, then I'm saving this wire. This fuse will melt, and just have to put a new fuse wire. Okay, so the purpose of this fuse wire is to prevent high currents. Okay, so that the wire is protected. So this sort of high current will happen if you have a large number of devices connected to this between these two terminals. Another way the current can go high is by mistake, there is some connection between this positive terminal and negative terminal. When you have this sort of connection, the amount of current flowing here is very high, right? Because current is V by R, and the R of this path is very, very small because it's like a conducting wire which is connecting these two lines. So this is called short circuit. Okay, once this happens, this current will increase. This current will be very high. So this current will become very high. So when this happens, this fuse has to melt first before this wire melting, because the melting point of fuse is low compared to melting point of this wire. So that way this fuse will melt and the current will stop flowing. Then you have to remove this short circuit and then put the fuse again and then turn it on. Okay, so this is the purpose of having fuse wire to prevent high currents, and high current can happen because of two ways. One, by design itself, we have too many devices connected across this one, and all devices are working at the same time. Okay, another is by mistake, I connect this positive and negative terminal. This is called short circuit. So that's what they would say. This current can go up because of two things. One is, the first one is called overloading. I have too many devices across the positive and negative terminals. Second one is short circuiting. By mistake, I connect a live wire and the neutral wire. Okay, these two ways the current can go high. That time the fuse should save. The fuse should melt and save the circuit. Electric
Sir,
prevents the electric current. What is the doubt?
sir, is it possible to short circuit by keeping a piece of metal that connects the positive and negative terminal of a switch?
Possible. Usually what happens is some device is connected. No, inside the device, some short will happen. So that way, short means a perfect conducting path. That way, this and this are connected, right? With zero resistance. Okay. For example, this is connected to an iron box. Something has gone wrong inside this iron box. So this iron box is connected across these two. Okay. If the normal working iron box, there is some resistance between these two, but something has gone wrong and there's some shorts happening in this device. So that will make this give a zero resistance part, which is basically short circuit. Okay. By accidentally,
Okay,
if
sir.
you place a metal joining this thing and this thing, then obviously this is short circuit, so this will increase the current. But what actually happens is, whatever device is connected, something goes wrong here, and there is a short circuit or a zero resistance path created. That will increase the current.
Okay, sir. Thank you, sir.
Just 1 minute left. So I think that, yeah, this is the last topic of this 10th standard. Fuse is most important safety device used for protecting circuits due to short circuiting or overloading. So current can go high because of two reasons. One is overloading, you have too many devices. So one way to avoid overloading is to have three phase. If you have three phase, means I have three-way, two more wires available. Okay, so I can split the number of devices along these three lines. This is actually one phase. This is single phase. Similarly, I have second one and third one. So suppose there are 15 devices. I'll put 5 devices in the first phase, second 5 devices in second phase, and the third 5 devices in third phase. Okay, that way I can reduce the current or overloading. Short circuit, if it happens, means obviously the fuse has to break.